Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 9. A ball of mass m makes a head-on, one-dimensional elastic collision with a second ball at rest. If the first ball rebounds with a speed equal to 1/4 of its original speed, what is the mass of the second ball in terms of mass m of the first ball? We use the fact that in all collisions, total linear momentum of the system is conserved. Namely, initial total momentum of the system is equal to the final total linear momentum of the system. Or, in terms of the individual momenta, we have, with the formula mass times velocity for the momentum, we have mass of the first ball times the initial velocity of the first ball, plus mass of the second ball times initial velocity of the second ball, which is equal to mass of the first ball times the final velocity of the first ball, plus mass of the second ball times the final velocity of the second ball. Note that this is a one-dimensional collision, therefore we can use positive and negative directions for the vectors. Initial velocity of the first ball becomes positive 4v. Here m1 is given by m. We know that the second ball is at rest initially, so v2i is 0. The final velocity of the first ball is negative v. And because we don't know the value of the final velocity of the second ball, v2f, we write positive v2f since it is to the right. If we rearrange this equation, we obtain 4mv equals negative mv plus m2 times v2f. Negative mv goes to the left hand side, so we obtain m2 times v2f equals 5mv. In addition to the total linear momentum conservation, we state that in elastic collisions, total kinetic energy of the system is conserved. That is, initial kinetic energy is equal to the final kinetic energy. Or initial kinetic energy of the first ball plus initial kinetic energy of the second ball. This is equal to final kinetic energy of the first ball plus final kinetic energy of the second ball. With the formula 1/2 m times v squared for the kinetic energy, we have 1/2 m1 times v1i squared plus 1/2 m2 times v2i squared equals 1/2 m1 times v1f squared plus 1/2 m2 times v2f squared. Initial speed of the first ball is 4v and initial speed of the second ball is 0. Final speed of the first ball is v, and after the cancellation of 1/2 on both sides, we obtain 16m times v squared equals mv squared plus m2 v2f squared. mv squared goes to the left hand side, so we obtain m2 times v2f squared equals 15m times v squared. Now if we divide the corresponding sides of equation 2 by those of equation 1, we obtain, after some cancellations, we get the final speed of the second ball as 3v. Now we put equation 3 in equation 1, that is m2 times 3v equals 5mv. v's are cancelled, so we obtain mass m2 as 5m over 3. B. With the same balls, another head-on, one-dimensional collision with the second ball at rest again, takes place. If the second ball moves off with half of original speed of the first ball, what fraction of the original kinetic energy gets transferred to the second ball? Here we are asked to find delta Q2 over K1I. Delta Q2 is the kinetic energy transferred to the second ball, and K1I is the initial kinetic energy due to the first ball. The change in the kinetic energy of the second ball can be written as the difference of the final and initial kinetic energies of the second ball. Since initial speed of the second ball is 0, so is the initial kinetic energy of the second ball. We obtain the ratio K2F over K1I. With their formula, we can write 1/2 m2 times v2f squared for the final kinetic energy of the second ball, and 1/2 m1 times v1i squared for the initial kinetic energy of the first ball. Here, 1/2s are cancelled. m2 is 5m over 3 as we have found in part A. v2f is v. m1 is already m. And v1i is 2v. Here m's are cancelled. Also v squareds are cancelled. Finally, we obtain 5 over 3 times 4, or 5 over 12. As a result, we obtain approximately 0.417. This is the fraction of original kinetic energy which gets transferred to the second ball. Okay, this is the end of the discussion of this problem. Thank you for your attention. See you in the next video.